Hello, my name is Byungmin Kim from Triple IXR Lab. Today, I'll be presenting the paper titled GigaHands, a massive annotated dataset of bimanual hand activities, published in CVPR 2025. This work focuses on capturing the complexity of everyday activities involving both hands. Understanding and replicating human dexterity, especially the intricate manipulation involving both hands, remains a significant challenge in AI and robotics. A major bottleneck hindering progress in this area is the lack of suitable data. Specifically, there's a shortage of large-scale, diverse, and accurately annotated 3D datasets that capture natural bimanual activities. Existing datasets often fall short in terms of 3D accuracy and realism. For instance, marker-based capture systems can lead to unnatural interactions and may lack visual realism. Markerless systems, while more natural, can suffer from issues like depth, ambiguity, or heavy occlusions, resulting in inaccurate 3D reconstruction. Data captured in the wild often lacks reliable 3D information and faces challenges with object tracking and camera calibration. Beyond the scarcity of data, existing datasets also face limitations concerning the annotations themselves. First, 3D hand or object shape and pose information can often be missing or inaccurate. Second, there's frequently a lack of semantic depth. Training text conditions models effectively requires detailed atomic text descriptions like crack a neck or tie a shoelace, which are often absent in current datasets. Finally, the dynamic nature and temporal consistency of bimanual coordination are often poorly captured. To address these multifaceted limitations, the authors introduced GigaHands, aiming to provide a foundational datasets for the field. The main contributions of this paper are as follows. First, it presents GigaHands, a large-scale and rich 3D bimanual activity dataset. It features accurate geometry, detailed atomic text descriptions, and high diversity, which is crucial for training large AI models. Second, it introduces the instruct-to-annotate pipeline, a scalable and efficient method for data acquisition. Third, the paper demonstrates the utility of GigaHands through applications such as 3D hand motion generation, head motion captioning, and dynamic semantic scene reconstruction. So, let's delve into the scale of the GigaHands dataset. This dataset is truly massive. It encompasses hundreds of real-world objects across various scenarios and scenes. The total captured duration covers many hours of bimanual hand activities. Furthermore, it provides thousands of motion sequences and annotated clips. These are paired with tens of thousands of augmented text descriptions, significantly boosting textual diversity. In terms of 3D pose data, it includes millions of bimanual 3D poses, complete with key points. This information is derived from RGB frames corresponding to an even larger number of unique hand images. GigaHands stands out not only for its scale, but also for its diversity. The TSNE visualizations here illustrate the pose and motion diversity. The left plot shows the distribution of 3D key points for both hands, while the right plot shows the distribution of VAA latent codes representing motion. Different colors represent different datasets. As you can see, GigaHands, the blue dots, covers a significantly broader and more diverse pose and motion space compared to prominent existing datasets like Taco or Arctic. Now let's look at the instruct to annotate pipeline, which is central to the dataset's construction. The first step is parsing. To ensure a wide range of activities, the authors started by extracting a large number of atomic level verbs from existing hand activity datasets, such as Ego4D and Taco. Hundreds of these verbs were collected and analyzed to form a comprehensive verb pool. The second step is grouping. Here, the extracted verbs were associated with interactive objects, and these pairs were grouped into realistic scenarios like cooking, crafting, or office work. Large language models were employed to perform the semantic reasoning needed for this grouping. For example, the verb beat might be associated with an egg in a cooking context, but with a drum in an entertainment context. The LLMs help infer these natural object-verb scenario combinations using common sense reasoning. The third step is structuring. Within each scenario, activities were organized into coherent scenes. These scenes were designed to feature objects that naturally co-occur. For instance, a making tea scene would logically include objects like a teapot, teacup, and tea bag. The fourth step involves script generation. Using the structured scene information, the authors instructed an LLM to generate time-sequenced atomic actions. Crucially, each action was accompanied by a detailed description suitable for guiding a human actor. The fifth step is filming. The generated text scripts were converted into audio instructions and played back sequentially to the participants. Participants then performed the actions according to these spoken instructions. During this process, 51 cameras captured the actions simultaneously. An operator monitored the recording, issuing corrective instructions and prompting a retake if a participant's action didn't flow naturally into the next, or if there were errors. The final step is annotating. The filmed motion sequences underwent a human-in-the-loop process for annotation review and revision. Annotators corrected any actions not mentioned in the original scripts or errors from the LLM generations and segmented sequences into meaningful clips. Additionally, textual augmentation was performed. To enhance descriptive diversity, an LLM generated 5 alternative versions of each annotation, varying vocabulary and style while preserving the original meaning. Now, let's look at the key application experiments conducted to validate the utility of GigaHands. First, text-driven hand motion synthesis. This involves generating realistic 3D hand motions from input text descriptions, evaluating the text-to-motion quality. Second, hand motion captioning. This task takes a 3D hand motion sequence as input and generates a descriptive text caption, evaluating the motion to text quality. And third, dynamic radiance field reconstruction, leveraging the dataset's dense camera views to render novel views of dynamic scenes. The figure on this slide illustrates that models trained on GigaHands can generate more diverse and accurate results for both motion synthesis and captioning compared to models trained on other datasets. To evaluate the text-to-motion synthesis quality, they employed specific quantitative metrics. For instance, they used R precision to measure how well the generated motion matches the input text description, and FID to assess the realism and naturalness of the motions, and metrics like diversity and multimodality to evaluate the variety of motions generated for the same text input. The experimental results clearly showed that models trained on the GigaHands dataset significantly outperformed models trained on other datasets across most of the evaluation metrics. The GigaHands-based model not only generated more accurate and semantically appropriate motions even when given text descriptions from other datasets, but it also produced a greater variety of motions for a single text input. This suggests that the large scale and the rich, detailed text annotations within GigaHands enable models to learn the complex relationship between text and motion more effectively. For evaluating motion captioning, the focus was on measuring the accuracy and diversity of the generated text descriptions. The examples here demonstrate the GigaHands trained model's ability to generate multiple diverse, yet accurate captions for a single motion sequence. Furthermore, it generated remarkably detailed and accurate captions even for motions from other datasets, showcasing strong generalization capabilities. This highlights how the diverse action data and detailed annotations in GigaHands contribute to the model's improved ability to understand subtle motion nuances and express them using rich language. Dynamic radiance field reconstruction, in particular, highlights a significant potential application enabled by GigaHands. The authors trained a 2D Gaussian splatting model using 38 of the 51 available views from GigaHands sequences as training data. The remaining views were held out for testing. As you can see here, the model successfully renders novel viewpoints that are remarkably similar to the real images. This holds true even for complex scenes involving intricate hand motions and interactions. It strongly demonstrates that the dense multi-view data provided by GigaHands is highly effective for dynamic scene understanding and synthesis. In conclusion, this paper presents GigaHands, a dataset offering unprecedented scale and richness in the domain of 3D bimanual activity data. It provides accurate geometry, dense views, and detailed atomic text annotations. The authors introduced the Instruct to Annotate pipeline, a novel approach leveraging LLMs and robust, automated 3D tracking, enabling scalable and high-quality data creation. GigaHands opens up novel applications demonstrated through experiment in motion synthesis, captioning, and dynamic scene reconstruction like 2D Of course, limitations exist. Data, co- data collection was confined to a studio setting, and the fully automatic tracking of highly complex or deformable objects remains a challenge. Future work directions mentioned include dataset expansions and algorithm refinement, potentially enhancing fields like robotic manipulation and human-computer interactions. This is the end of the presentation. Thank you for your attention.